Good morning, everybody. Welcome to the second day of this half of the 2024 International Colloquium. Our first speaker is Mitsuhiro Shishikura of Kyoto University. This is a talk that is being supported by T&Q. Professor Shishikura will be speaking on, well, the title is up there, Rescaling Limit of Quadratic Rational Maps and Trees of Spheres.
Thank you very much. So I'd like to thank organizers for giving me this opportunity to speak here and to come to India first place. And I'm sorry for the people who have heard similar talks before. But anyway, I don't have a great theorems, but I just want to share with you some basic ideas about how to deal with this degeneration of rational maps and introducing some kind of trees and spheres and so on. Okay, let me start. So I'm going to talk about degeneration of rational maps of one dimension. So acting, and so basically I'm more interested in non-polynomial maps, the rational maps which cannot be polynomials. And before starting, let me say some motivation here. So originally, my motivation was somewhat different. So initially, I worked on quasi-conformal surgery for the rational maps. And with surgery, you can do many things, but one of the things is that given some problems about the fatigue component and so on, then you can just show the existence. You can actually construct some rational maps using the surgery technique. And then once you show the existence, there's a question is, can you find it somewhere? Well, what family can find it and so on. And to answer those questions, it is easy to consider the limit of certain quasi-conformal deformation. And that will help you to locate what you constructed. I'm showing you this in a minute. And another motivation is kind of long-standing motivation. That's a Sarston's algorithm for finding rational maps with a given topological data. And this I will explain in a minute also. But well, there are two cases in Sarston's theory, and in one case it's equivalent to rational map. The other case, basically it is related to the iteration and time space, and it diverges in the time space to the boundary, and this leads to something called the Sarston obstruction. Okay, so both cases are related to some limit, and the limit can be related to a tree and the piecewise linear map on such a tree. So I try to promote the word called the tropical complex dynamics. So the tropical being somewhat fancy. And also this is piecewise linear, really piecewise linear dynamics that coming from complex dynamics. And well, today I'm going to relate this to other situation where, again, related to the degeneration of maps. Okay. So let me just say a little bit more about the motivation, because that shows you how these three objects can be related. So given certain data about the fatigue components of rational map, and ask, you can ask whether they can be realized by a rational map. And when they can be realized, you can ask for what degree you can realize or what family you can realize. Okay, so two examples. First one is about the Hellman rings. I have been working on this for many years. So this picture shows this is a sphere. And the Hellman rings, for those who are not familiar with the complex dynamics, it is an annular region on the sphere. And this set must be a periodic of certain period. And if you take the return map to this annulus, it must be conjugate to the irrational rotation on annulus. So here I'm drawing in colors 4 annular domains. And I assume that there are some orders that you try to permute, and ask whether this is realized in the rational map. Okay, also under certain conditions, you can realize that I think one easy thing to imagine is that when you have an annulus, there's something called the quasi-conformal deformation. So you can create a different rational map with the same topological dynamics, but with a different conformal data. So the most important conformal data for here is the modulus of the ring. And you can deform within the family of rational maps the annulus so that the modulus tend to infinity. And what does it look like? So annulus here is very thin, but when you make the modulus larger, it will look like a really long cylinder. And that develops the sphere into the shape where it's like a union of many long cylinders and then intermediate regions between them. Okay, so eventually, when you look at the long cylinder as just a segment, it may look like this. So, for example, if you have this configuration for 4, then this annulus corresponds to this annulus corresponds to this one, and to others in a similar way. So, if you have a different configurations, you have a different the tree-like object. So here on the trees, the edges correspond to the annulus, where you make it a cylinder, and then you crop the cylinder to become a segment. And actually, to construct those objects, it's easy to start with those objects. Then you add some intermediate information in between so that you can extend them as a, first of all, topological map. And then you do surgery technique, checking several conditions to go back to the rational map. Okay, so construction, it's easy to start with those objects. And also, for example, when you realize you can count the number of critical points and so on to check if it's realizable for like a cubic rational maps or quartic rational maps and so on. And this is one thing I came up earlier. The second example is even simpler. So look at the periodic Fatou component or pre-periodic Fatou component, and say this has 4 complementary components. And well, for periodic ones you cannot realize, but for pre-periodic ones, strictly pre-periodic ones, you can realize. But again, you can ask whether you can do this for a certain degree rational map for certain family and so on. Again, it's easier to think this as a tree like this. So here, the domain kind of you shrink this. If we have annulus, you shrink the similar way as before, and the boundary will correspond to the vertices of this graph. So somehow from this, you just imagine a graph like this, and you have to embed this into a dynamics. And if you are successful, you can create such a Fatou component, okay, for given n. And so this is a way you can associate some kind of tree from complex dynamics. Okay. Another famous situation is a Sarson's theorem. So now I'm not assuming that the map is holomorphic. It's just a topological branch to covering of a degree greater than 1, which is orientation preserving. And so there can be a critical point. So look at the critical orbit, for the critical orbit, P sub f, like this, and assume that this is a finite. So critical points have a finite orbit, okay? This is called a post-critically finite. Then there's a Sarson's theory starting from here. So take 2 such maps, assuming the same conditions. And then question is whether 2 maps can be equivalent in the following sense. So 2 maps, F like this and G like that, are equivalent if you can find the 2 homeomorphisms that makes it commute. And then additional condition that this post-critical set correspond, and they are homotopic or isotopic relative to this post-critical set. And when this happens, we say F and G are equivalent or Sarston equivalent. And the question first asked by Thurston is when you are given this topological branch covering, when is it equivalent to a rational map? So rational map, when it satisfies these conditions, of course, this is a PCF map, then can you find a rational map of this type, okay? So Thurston's theorem, I'm not stating this theorem itself, but gives an answer to this question in terms of multi-curves in the complement of this post-critical set. And when the answer is negative, there must be some multi-curve with certain properties. So let me explain this in next slide. So essentially, I'm sorry that only talking about the small part, but the Thurston theory says that you take a sphere minus the post-critical set of F, that's a finite set. So it's a sphere with a finite number of punctures. Then you can consider the Teichmüller space of such an object. Then the map F induces a self-map of such a Teichmüller space. And the key point in the Thurston theory is that F is equivalent to a rational map. That means a positive question to the previous question. If and only if the orbit under this sigma F, the self-mapping Teichmüller space, stays bounded. Okay, so one orbit is bounded, then all other orbits are bounded. Okay, and if the orbit is not bounded, in fact, it can be shown that the orbit by sigma F tend to the boundary of the Teichmüller space. So that means for each point in Teichmüller space, you have a Riemann surfaces associated Riemann surface structure for this sphere minus finite point. And these Riemann surfaces go to the boundary. That means they degenerate in some sense. But the sphere with finite point removed, what can happen when they degenerate? Well, a kind of several points may collapse, or you can say that this is like one way to say is that you remove they degenerate. One way to say is that points kind of approach to other point, but other way to say is that there are curves in this Riemann surface structure that becomes shorter in hyperbolic distance. And this is a way, if they're short, you try to draw the picture like this. And that goes to the picture which looks like a tree. So this is a topological picture with some points marked in a complement. But when the structure goes to the boundary, well, again, it's similar. The curves shorter, that means surrounding annulus becomes a very long cylinder, and they should look like this. So that means it's easy to associate a tree-like object. Okay, these are the ideas which appeared earlier, and then today I'm going to talk about another thing which is related to the degeneration of rational maps. All the cases are related to the degenerations. And I think among these speakers, there are Laurent and Charles and Dima and Misha who worked on this. And I think Dima's talk, he also talked about the degenerations, but in a sense, it is also going in direction to this degeneration. But I think in many situations, it is important. So I will talk about especially the rescaling limit. This is one way to look at the degenerating families, because when it degenerates, if you look differently, you may see different things. And then I will talk about the associated trees of spheres, and then the related dynamics on a Berkovich space for a Laurent series field, and the realization problems. And there's more recent ones about PEL-N, which is in the family of the space of a quadratic rational map, where one critical point is periodic of period n. Okay, that's called PEL-N. And there are work by Caroline Davis and Alex Kapiyama and Eiko Hironaka. And so I worked with Eiko Hironaka last summer for studying period F4 and period 5. And I'm going to show you some worked out example for period 4 and 5. Okay. So first, how to see the degenerating rational maps. So first of all, space of rational maps of degree D is embedded into 2D plus 1 projective space. But you have to delete this hypersurface where the denominator and the numerator have a common factor that defines the hypersurface. And then you take the conjugacy class in a moduli space, which is conjugated, quotiented by the Möbius transformations. So the generation means that, well, not here, but I'm speaking here. You are going to this hypersurface H where the things degenerate because you have to factor out the common factor from denominator and numerator. So what happens if you go approach the one map on the H? Okay, what happens is that well, near the common factor or the zeros of common factors, basically nothing happens. So you have a uniform convergence. Well, the limit itself may be a constant map, but anyway, you have convergence. But near the zeros of common factors, the dynamics is drastic, and there can be something wrong going on. Okay, that is the picture. So, well, one way to see this, the limit is, of course, you can see this limit in H, but you are losing too much of information there. So I try to recover some information for this sequence. So this limit, as you degenerate, it is very sensitive. So I didn't talk about here, but I didn't talk about the quotient by Möbius transformations because the result depends very sensitively on the coordinate changes. Basically, what you see as you degenerate depends on where you are standing. So for rational maps, to specify where you are standing means that, well, up to Möbius transformation, you can normalize 3 points. Okay, once you normalize 3 points, because that specifies where you're standing. But when you the sequence is degenerating, it may happen that the normalization of 3 points may be differ. So then you're going very far, and you're looking at a totally different thing from the original ones. So in that sense, you take this, the family of a Möbius transformation and conjugate them. So then after the conjugation, it may go to some limit, but F and G may have a very little in common in general for degenerations. If there's nothing happens, that's not degenerating sequence. Okay, so for this, are there dynamic meanings? So in general, if you go to here, it's very much likely that you may have just to see the constant map or degree 1 Möbius transformations. So you're missing some things. So instead, you want to recover some dynamical information for this sequence. You may take some number q greater than 1, and you iterate the original family q times, and then change the coordinate by some Möbius family. And then there could be some limit. So it seems strange, but just to assume that that can happen, and it does happen, then, well, this limit also carries some information from the original one, which may disappear when you just take the straight limit. Okay? So what are the possibilities of this limit? And this is called a rescaling limit, according to Kiwi. And so, of course, there can be a constant limit. That's a trivial case, or Möbius limit, the degree 1. But we're interested in the case where this limit, the rescaling limit, is greater than, of degree greater than 1. And, well, post-critically finite, I defined in previous slide. But that is also important. But for the moment, we are interested in more kind of drastic example of which critical point, some of the critical point may have infinite orbit. Okay. So as I defined, the scaling limit is you iterate the family and change the coordinate and ask whether there is a limit. So there's a work for quadratic rational maps. And he says that there are possible rescaling limits and say that they look for the non-post-critically finite ones, and he classified in two ways. One is that you have this limit, and the limit must have, so I'm assuming that limit has a degree greater than 1, and say that this limit has a parabolic fixed point. That's one case. Second case, it's overlapping, but I try to separate them because I think it is related to different phenomena. And this first part is similar to the previous case, but here you can have another limit for different period, higher period with Q prime, and it has a limit, and the limit is a polynomial. Okay, so well, just looking at this, it's kind of difficult to get what it means, but I'm telling you in a while that what does it mean if you organize everything with the trees and spheres. Okay, and let me discuss about the non-PCF properties. And if you can mark some of the orbit, like a critical orbit, then well, in general, they can be separated some curves. So say critical orbit or periodic critical orbit. Then in general, when you have families, they can be separated the curve which are pinched like this. So that means if this is the sphere, if you take these 4 points, which are here in previously, but the cross ratio as 4 points in the Riemann sphere, they are characterized by cross ratio of 4 points, and the cross ratio degenerates. That means goes to 0, 1, or infinity. Okay. So when the spheres are kind of degenerating and they are pinched by several curves, they look like a tree. So that just like I explained before. Okay, and so here, for example, this case in Kiwi theorem, it involves the two different coordinate changes. First, the coordinate change MT, and the second coordinate change MT prime. And looking at the different coordinates means you are focusing on the different parts of the original sphere. Okay, as parameter t goes to 0. Okay, so there's a work by Mathieu Arfeux about rescaling limits. So it's not good way to look at the separate rescaling limit, but they should be organized as a tree of spheres, or I would say trees plus some spheres at some of the vertices. Okay, and the return map to some small spheres correspond to the rescaling limit. So this is the way. So so this is, well, I haven't defined this tree of spheres, but basically this is coming in. So essentially you have trees, but in addition to the trees, at each vertices, you are supposed to associate some spheres, and I call them small spheres. And maybe here, there are only two edges coming out, but still I may associate, or at the end of the extreme vertex of the trees, you may also associate a sphere. And this is such an object, but since it's coming from the dynamics, you want to have some dynamics. So on this tree, you want to have some map. And also on small spheres, there should be some corresponding maps. That's the object you associate. And what's coming is that, for example, this one is fixed, then you can define a return map. So for example, this sphere may be a period 4. then you can define the fourth iterate that defines the return map. And actually, in Kiwi's theorem, the scaling limit correspond to these the return map of the small spheres. Okay. So this tree should be considered not just well, in a degree 2, it's not so obvious, but in general, if you continue to a higher degree, it's natural to consider this tree as a metric tree, and the map is a piecewise linear map. So there's going to be a naturally induced map, but since it has a metric, you have a derivative or stretching factor, and the stretching factor has to be integers. And so just like before, when you look at the edge, you should imagine that so maybe I should say, explain a little bit more. So if we see this and with small spheres, you just blow up this edge to a cylinder like this. And then you join them with the small spheres with some hole. At least topologically, you can construct it this way. And so whenever you see it, so you just imagine a topological sphere of this type.
Recording in progress.
What was wrong? So I should have to share. Sorry, I think I clicked something wrong. So, okay. Yeah, so when you see this picture, you should imagine what you have is something like this, right? So what is the data now? So the object we are looking at is a tree with a piecewise linear map. So I assume that this is a finite tree with a metric, and the map defined on the tree should be piecewise linear map. Okay, so maybe, for example, we are working on a quadratic case, then most of the places you have a degree 1, so that means it's isometric. But here, you may have a degree 2, where I indicated with double lines. Then this edges will stretch by a factor 2. And so this gives you some kind of consistency condition for I think I should share this one. Yes. And then another data I need is the small sphere for each vertices. So for example, in these pictures, I'm indicating blue cycles and green cycles. So blue is here, it's period 3, and green is period 5. And after 1 goes here and then come back to 1. So each one is associated with the Riemann surface, small Riemann surfaces, and this red point will go among, so correspond to this edge. Then this edge, if this edge goes there, the corresponding point should go to the corresponding point and so on. So it's consistent condition with the tree map. And then when you have an edge with degree 2, then this point should map the corresponding point in a blue sphere, but this point must be a critical point of degree 2. And so on. It's the same thing for this one. Here you have to have a critical point which goes there. Okay, so this is the data we need. And so actually, when you have degenerating families of certain conditions, you can actually associate such an object. when there is non-trivial rescaling limits. Okay, so here how to interpret these maps. So for example, on this tree, I'm assuming that this part is rotating and degree 1, degree 1, degree 1, and this part goes over, this sphere goes here, and so this edge must go to there, okay? So it may look strange that because this edge just go over to this edge, but again, if you use this interpretation, you should imagine that you have associated cylinder to this edge. It's not the segment, but it's a cylinder. So you just make a whole stretch a part of this cylinder so that in the image, it's not just covering this, these edges, but stretch in the middle part so that you can cover everything in here. So everything in here should be covered by its image. And similarly, from there, sorry, I'm not up to the reaction. Well, the same thing for here. So the image, this sphere should go there, and this sphere should go there. So the image should cover everything in between, including the branches coming out of these spheres, so that, for example, you just to stretch this tiny disk into the bigger ones so that it covers those branches. Okay. Mathieu Arfeux says it corresponds to the Jean-Kiwi's first case. For degree 2 case, there should be in the middle some tree of the star pictures. So some fixed point and some say Q branches, and they are rotated like a P over Q rotation. So the middle part is just very simple, so isometric and the rotation, and at the end of this star, you have to have these periodic spheres, and the edges correspond to a point on the sphere for which this is periodic, and the return map gives a parabolic fixed point for this return map. That's a specific thing that is obtained. And so if you remember Jean-Kiwi's theorem, the return map, the first case return map, must have a parabolic fixed point. That's why you have it here. Okay. And then, so I didn't color the central point on the star, and you have to have a fixed point over there. But if you take the return map, then this is just a periodic rotation on the small sphere. So it is a Möbius transformation, and it's a period 3 Möbius rotation. Okay. And here, just as I said, it's a return map has a parabolic fixed point marked at red. And then there's another cycle of sphere, the green one, it's a period 5. And this point corresponds to this one, this one, this one, this one, and come back here. So that means it's a fixed. And I marked this as a degree 2. So it's a critical point and fixed for return map. So it has to be a polynomial. So this is a second part in Jean-Kiwi's theorem. And this is the way you can visualize what he said in his theorem. Okay, so double line is degree 2. So the realization problem, I'm working with Mathieu Arfeux, Jean-Kiwi, and so in general, degree 2 or higher, suppose you have this picture, then can you realize a family of rational maps so that this degeneration gives you this given data? Okay. So we have many worked out the case, but we haven't got to the point to state in a theorem in general. Okay. So one way to look at this is through the theory of Berkovich space. I'm not a specialist in this theory, so if you have questions, I can point you can ask. to whom you can ask. Okay, so starting with algebraic setting, the algebraically closed field, which has a non-Archimedean. Did I say non-Archimedean? I should have said that with some variation that the project space is nice, but not locally compact. So you have to introduce a better space to work nicely. That's the Berkovich space. I don't have ability to define all those things, but what essentially has is that you have some space. So, well, from the field you can have the projective space, but that comes as a boundary point of this Berkovich space. And inside, there's some different object from P1 of K. And the structure there is basically the tree-like structures. So basically, there are infinite trees. Even from one point, there are infinitely branches sticking out, and infinitely many branching. But at least this is a simplified picture. And so essentially, whenever you have some object for the K, you may have a chance to look at the Berkovich space. Okay.
Is it compact too?
Yes. And also, the middle part looks like a tree, so it's easy to handle all the analysis.
So essentially, it's an uncountable boundary.
Yeah.
That is the
Yeah.
projective.
Even the branching is uncountable, so it's a bit scary, but somehow it has some nicer properties. And say, as a field, I'm only looking at this field of formal Laurent series. And the formal Laurent series is a bit too small. You may go to this Puiseux series, and then you have to take algebraic closed field. Which way? That completion and algebraic closed closure. But anyway, for the moment, I just look at the formal Laurent series. Suppose you have a rational map, which is defined with the coefficients in this Laurent series field. And then there are two ways to look at. So of course, algebraically, you just have a coefficient in this field. But also, since this Laurent series field has a variable, so you can consider this as a family. Okay? Especially the coefficient in the Laurent series is complex numbers, then it will define a family of complex rational maps. Okay? The two ways, it's important to look at two ways. And then, especially if you have a family, there is a chance that you can look at the families of rational maps, and when t goes to 0, it may degenerate. And actually, many important, interesting families do degenerate. So anyway, at this stage, in general, you can define this mapping between the Berkovich spaces. And so picture is like this. It's oversimplified, and I'm not looking at the even Puiseux series, only Laurent series. But they are located like this. So, for example, there's a point 0 and infinity, and there's some central point called the Gauss point in the Berkovich space, which is situated somehow centered. But for example, 1 maybe some on the boundary, and other things, it's coming from the Laurent series, so maybe a Laurent series of some type, maybe here. Well, all Laurent series with many types of coefficient will situate in the branch sticking out of somewhere, or Laurent series starting from T will come here, and with different higher order coefficient will be branched from somewhere, but with the same first coefficient, you are going into the same branch. It's the same thing for here. Starting from 1, but it's branching at some order. It's branching from here, from the direction 1, and here it's for negative powers. Okay. So what's the map here? So just look at the quadratic map. Z goes to z squared. So then for this map, basically this is like a degree 2 lines that mapping is stretching by a factor 2 and onto this line. it's fixed as a line. And then there are many branches that, well, two branches may go to the same branch. And if it's a quadratic, the image is like this. So the position of this image will be changing. But you can just visualize what you have as a map on Berkovich space as a mapping on the tree. This is connected to what I described before. Okay. So let me go to some specific part here. So, so I try to apply this to a problem for the quadratic rational maps. So I try to work on this per n. So per n is the space within the space of rational map. So here I need to, so quadratic rational maps have two critical points. So I need to mark two critical points. So they are not interchangeable. And then you define the space of rational map with marked critical points. Okay? And then the per n is the set of maps for which first critical point is periodic of period n. So it's a super attracting cycle of period n. Okay? So there are some questions floating around about the per n and for example, irreducibility or genus or how many punctures. So, well, in general, this is the Riemann sphere, finite Riemann sphere with some punctures and how many punctures there can be. Okay. So, what is a puncture if you consider this? So, of course, this, as described before, f can be defined as a point in the projective space. So it may degenerate, and actually the punctures for per n should correspond to a degenerate rational map. So near the punctures, if you take a family, it should be a degenerating family. And then what I'm going to explain now is some information about trees and spheres. And I'll show you some pictures drawn by Hironaka for this one. So what are the correspondences and what's the possibilities for this side that can come up? For pair 1, 2, 3, they are relatively easy. So let me skip and go to n greater than or equal to 4. So that means first critical point should have value n, which is greater than or equal to 4. And well, these three people try to look at this family, and they came up with certain parameterization of the families. So of course, as I mentioned to you, it is important to normalize 3 points on the sphere. So we are going to fix 3 points. And well, the key is that, well, once you try to fix 3 of them, then well, you are restricted to the view from that point, and you may be losing some information by doing it. But anyway, to work on some concrete families, you have to fix 3 points. So now the normalization is that the first critical point is at 0, and then it goes to the critical value, which is normalized to be infinity, and then infinity should go to 1. Okay, this is a normalization. Okay. Then introducing 2 other parameters. So these are just a normalization. Then there should be some point which goes to x, the 0, so that is called x, and 1 should go to y. Well, in general, this is not critical point. There may be 2 choices, but at least this gives you a way to write down a rational map with the 2 parameters x and y. Okay. And so it's easy to calculate the rational map with these properties. So it can be written like this. So since I'm assuming that the n is greater than 1, so this cycle should have a period greater than 4. So x cannot be 1. So y minus x is are there. You can notice. Okay, so the parameter is taken as in the P1 cross P1, but well, some cases like x equals 1, the map degenerates. So you have to remove some subsets from the product, okay, so that the f has a meaningful things. So where should you remove? Okay, so obviously when x equals 1, I said you have to remove it. But when x equals 0, then you have a cancellation to lower degree. So that's you have to remove. It's a the way it degenerates. Okay, and also x goes to infinity, you have to remove. And also another information is y equals infinity and x plus 1 equals 1. Again, if this is 0, then you have a cancellation. So within this parametrization, you can say pair 3, what the critical point is periodical period 3, characterized as y equals 0. And pair 4 can be characterized as x equals y, because if they are equal, this gives you a cycle, super-attracting cycle period 4. And when y equals 1, that means this one is prefixed. So that shouldn't happen for pair n, because you are supposed to have a periodic cycle for critical point. Okay. So these are the things you have to remove. And so that means when you approach to these places, the rational map is going to degenerate. So that is our interest. Okay, so let me just draw here. So in P1 cross P1, you are removing the y equals infinity, and so this side x and this side y, and x is equal 0, x equal 1, and x equals infinity is removed, and also y equals 0 is going to be removed if n is greater than or equal to 1, and y equal to 1 is also removed. And the additional thing you have to remove is here. X plus y equals 1. Okay. This is a parameter space we are going to consider. And then in particular, the pair 4 stays in here. Dotted line stands for the pair 4. And so for this one, there are punctures corresponding to this, and there are 4 of them coming here. Okay, for this family. Yeah. So the punctures I showed you. So let's see. So within this family, if you approach to the punctures, what happens? And there should be associated trees of spheres, and see what you get. So let's see what's the candidate. Yeah, later I show you some pictures for pair 5. But for pair 4, this is one possible picture. So there are 3 other cases I show you. But I said that there should be a star in the middle. And this is isometric, and just here it's a flipping. And there should be a parabolic fixed point for the return map. And then additionally, you have these branches. So this one goes over here. This one goes over here. And this one goes over to here. This one goes over to 4. And this one goes over here. Okay, this is a picture. And add x1 and 0, 1, infinity, and x. So that's related to the point where this dynamics is specified. 0 should correspond to a critical point staying here. It goes over to infinity, and 1, and so on. There should be another critical point because of its end at the end of these degree 2 edge, but that is not specified because actually for return map, you have to have a parabolic point. So there should be a critical point attracted to the parabolic fixed point. So this one has an infinite orbit. Then inverse image of 0, you have x, and image of 0 is infinity. Infinity goes to 1, and so these marking correspond to those points. Okay, so the blue sphere is period 2, and I normalize everything so that 0, 1, infinity are specified this way. So that means looking at these three structures, this light blue sphere is a branching point toward the 0, 1, infinity. So no other point separate these three, because here, if you look at from here, 0 and infinity are in the same direction, same branches here. It's the same looking at from here. 0 and 1 are in the same branches. So in a sense, for these 3 points of normalizations, this is like a central point. So that corresponds to the Gauss point and Berkovich space. So let me suppose that the distance between these. So there should be a metric introduced, and there is some ambiguity for normalization of the length up to scaling. So just let me assume that this distance is the length 1. So this is 1/2, 1/2. So, and in Berkovich space, I forgot to mention, but you can associate the length or the metric by the difference of the powers. For example, I draw something like this, 1 infinity, and like a C1t, the first order, C2t squared, second order. So the difference of power here is reflected here, and it will be length 1 if you interpret this way. Okay. But if you use a different power of t, then you may scale the metric. Okay. You have to have a degree 2 edge here. That means you have to have a critical point here. So that means on this sphere, the degree of the mapping on the small sphere must be 2. And it's the same here. You have a degree 2 edge. So the mapping here to there should have a degree 2. And on all other spheres, they must be a degree 1. Okay. So if this data is coming from the degenerating family, what happens? So degenerating family means that you have this type of the parametrization. And well, if t goes to 0, relatively these two distances go to 0 because t is going to 0. So that means if there's some edge from Gauss point to this one, these two branches, if you're looking at from here, they kind of collapse to each other. So that means this parameter should go to 1. This parameter x should go to 1. Okay. Well, there's ambiguity of parameterization. So in a sense, you can take this parameter t equals to 1 minus x is a new parameter of these Berkovich space parameterization. There's always you can always change the coordinate in the formal Laurent series so that it induces some automorphism on the space of Berkovich space. And so I'm taking advantage of this ambiguity to make this parameter 1 minus x. Sorry. So this was is saying that this degeneracy should correspond to x equals 1. So it corresponds to this whole. Okay. I think so. There are 3 other degenerations or puncture of the pair of 4. And they can be described by these 3 types of the trees. I think the convention is the same as before. Like in this case, you have sorry. I think something was wrong. Sorry about that. Okay, so forget about this. This is very simple. You have only stars in this case. But here, for example, you have a period 4. So for return map, the critical point is periodic of period 4. Okay. So I didn't have time to draw for pair 5, but in a similar way, you can construct a possible trees of spheres and the return maps. Because for these periodic ones, you always have a parabolic cycle, so it's very easy to determine. And so this is what we got so far, that I've been working on this project. So this is a picture drawn by Eko Hironaka for this space, because well, all these pair ends are embedded in this P1 cross P1. So for different periods, she used different colors, and this is of course pair 4 and there pair 5 and so on. And there are many interesting structures coming out from here or here, especially on the x plus y equals 1. There are some structures you can observe.
So this is a real size?
Yes, it's a real size. So sorry, I did forget to mention it's a real size. Okay.
So how much of the complex picture is contained in the real size?
I don't know. So there are. I don't have a complex picture, but there are, of course, like a mandible set like pictures. So there are many things. But in this case, you have only punctures are real. But in general, I imagine that there should be more complex structures outside real. Okay. But let me just mention one more thing. So you notice some interesting structure here. And that corresponds to some like a star. And on the star, you can have this rotation, rational rotation. And for each rotation, you can find the parameter easily. And so there should be, when they degenerated, they should have those parameters in here. That's a small claim we have worked on. And okay, so there are future problems to work on, but I think I'm up to the time, so let me stop here. Thank you very much.